Okay, this is Mr. Diller with the solutions for the Chapter 4 test review. Let's get started. Problem 1 is a related rates problem, and the giveaway for this is that the units are 2 feet per minute. So when we have related rates problems, we're going to take our derivatives and we're going to make sure that we put like a d whatever over dt after. So it wants to know how fast the area is changing, so we're going to use the area formula. So on this one it's going to be the width times the height, or that'd be like base times height. And you got to be really careful, you have to use the product rule here. Now listen, we've been talking about this a lot, that usually before we do a derivative we try to substitute so we don't have to do the product rule. But on related rates problems, there's usually not a substitution available. Cone problems you can do that, but other than that you're sort of stuck. So we really have no choice. But it's no big deal here, because if I do the product rule, I get dH dt and dW dt, which usually I'd be like, oh man, that's too much stuff. But here it's not a big deal, because I know what those are. I know that the height is going up by 6, and I know the width is going down by 2. So not a problem. Whereas on other problems it could be a real issue, and I would want to substitute. For this part, this would be a Pythagorean theorem thing. All you got to do is look at this. Look at the diagonal. Perfect. It makes a right triangle. So you're going to set up Pythagorean theorem. You're going to take your derivative. You're going to fill everything in. 13 is the hypotenuse that I'll be able to figure out here, because this is 5 and this is 12. All right, number 2. When we use differentials, we just take the derivative. Somebody asked me in class, well, what's the difference between differentials and related rates? Not a whole lot. They're pretty much the same thing, to be honest. The only thing is a differential doesn't have dt's in it like a related rates would. But as far as what you do, it doesn't really change anything. So I just fill in my numbers. All good. Number 3 is a problem where I'm going to have to use trig. And there's 2 possibilities here. You can set the problem up and go y over x. So here's y and here's x. And do the quotient rule. It's totally fine. Or you could realize that, hey, the tank's not moving, so 700 is a constant. And you could just put 700 right into the problem, and that'll give you a different derivative. Everything will work out the same. You're going to get the same answer either way. On this side, be careful. Remember that secant is the cosine flipped. So when I go over here, I've got 700 on the bottom, and that would be over 9126 for the cosine. And so I'm going to flip that. By the way, this side is 9100, in case you didn't get that, because the rocket traveled for 7 seconds at 1300 feet per second. Alright, that's a lovely shot of my kitchen table there. Number 4. This formula is coming from x squared is the area of the bottom, and then I got to pay $50 a square foot. Over here, there's 4 sides, and they're all x times y, right? This would be x times y, x times y, x times y, and then it's $30 a square foot. That formula I'm going to use because I'm trying to minimize the cost. So this is an optimization problem. In an optimization, I want to make a substitution. And so that's why there's extra information. That's what the 600's here for. So I take the volume, I set it equal to 600, I find out what y is, I plug it in. Listen, I don't care how difficult you think these problems are, if you follow the steps, then you've got a shot. All optimization problems mean that you are supposed to do a substitution, and then you must simplify before you take the derivative. I need to see that. Even if you mess that up, it's still important that you were trying to do that. Then you take your derivative, and then from here you can solve this by moving this stuff over to the right, kick the x squared back over by multiplying, divide by 100, and it'll all work out. On problem number 5, you have to make sort of a decision here. What is that 867 there for? Sorry about I was on a boat there. The 867 is the area. It's got square units. So that's why I'm linking that up with the area. I'm solving for y or x. It doesn't really matter. I'm plugging it in just like you do on every optimization problem. And then I go ahead and I simplify, and then after that it's derivative time and solving. I'm not really showing you all the work here. I'm just trying to sort of talk about what we're doing. You've got the solutions on the back of this. Alright, number 6. Our basic problem. We're going to see lots of questions like this. Probably not all combined into one question like this one is, probably split up into several questions. But the process is still the same. For increasing, decreasing, mins and maxes, I take my derivative, I set it equal to 0, and I solve it. And you might not think you can solve this, but you can. Add the 1 over, ln both sides to get rid of the e. ln of 1 is 0, add the 1 over, you're all set. And so according to my chart, remember you plug these numbers into the derivative. I get negative plus. For the second derivative, piece of cake, because the second derivative only has e in it, and e will not equal 0, it'll always be positive. And so this will be concave up, and it'll never switch signs, so no points of inflection. Alright, number 7, the dreaded cone problem. Every cone problem is done the same way. We set up a substitution. We either say that r on this one is half of the height, because it is, or we could say the height is double the radius. On this problem, I'm going to get rid of r because the information I have is about the height. I already know what h is going to be eventually when I substitute it in, and I already know what dh dt is. So r is sort of useless to me. I'm just going to get rid of it. Although, just so we're clear, if you got rid of h, you'd be fine because you know that r would be 3, because that's half of the height, and dr dt would be 0.1. So you could still work it out that way, but I didn't. So I put this half h in there, I simplified, I took my derivative, plug in the numbers. Number 8 is a quotient rule. Be careful. You get this eventually. Don't you dare multiply the bottom out. That's not what we do. Set the top equal to 0 and the bottom equal to 0. The negative 0.794 is from the top because it's the cube root of negative 1/2. The 1 is from the bottom. Use this whole thing to make your sign chart, although really all you got to do is pay attention to the top because the bottom's going to always be positive. Alright, number 9, mean value theorem. Take the derivative, take the average rate of change by plugging into the original. Take about 2 seconds to realize there's no chance on earth that you're going to solve this. So move this 0.322 over to the left side, use a graphing calculator. But I'd like to point out on this one, this graph is sort of funky. It really hugs the x-axis. And the first time I graphed it, I thought for sure I made a mistake because I couldn't even see the graph. It looked like it didn't even graph. So if you change your window to 1 and -1 for the y, you'll be able to see what the graph looks like. Alright, great. Last problem. Number 10. Alright, so this problem has the derivative graph in it. It wants mins and maxes, so I'm going to just go to the sign chart. So I make a sign chart from A to F. I note that the derivative, which is this graph, equals 0 here and here, and that it's positive, negative, positive. And so I fill in my chart, and I got my answers. To get points of inflection, I have to look at the second derivative. The second derivative is going to be the slope on this problem. So again, I can make a sign chart. I put C and E on it because that's where the slope is 0. And the slope is going down, up, down. So that's negative, positive, negative. So there's 2 points of inflection at C and E. Alright, that's it for this review. Make sure that you've looked over worksheets 411 and 412 because there's different style problems that we've talked about. But if you understand the stuff from this review, that's a pretty good sign that you're probably in pretty good shape. But it wouldn't hurt to be looking through some of those other problems. Alright, good luck.